Welcome. Suppose you have a bunch of radioactive atoms, say 12. You know from physics that the time until an isotope decays is exponentially distributed with a parameter lambda, depending on the half-life of the isotope. You measure for each of the atoms when it decays, and now you want to know what you can say about the value of lambda. Well, you know that the expected value of the decay time equals 1 over lambda. And by the law of large numbers, you know that the average decay time approaches the expectation after taking sufficiently many measurements. Thus, a good estimate for the value of lambda might be 1 over the average decay time. Formally, if you do a number of experiments with results x1, x2 up till xn, an estimate is a function of these outcomes. The important part here is that the estimate can only depend on the outcomes of the experiment and does not depend on the distribution from which these xi are drawn. This is necessary as we do not know the distribution. Otherwise, if the estimate would depend on the distribution, we would not be able to calculate the estimate. If we repeat the experiments on a different day, we get different values for these xi. Thus, the xi are in fact outcomes of some random variable, capital Xi. As the estimate depends on the values of the little xi, this means that the value of the estimate is also a random variable. This random variable is called an estimator and written capital T. Let us go back to the example of the radioactive atoms. 1 over the average is an estimator for the value of lambda. But is it a good estimator? To answer this question, we first need to know what we mean by a good estimator. As the estimator is random, we cannot hope that the result is always exactly equal to the real value of lambda. The best we can hope of an estimator is that it is close to lambda most of the time. Now, if the true value of lambda equals 10, then having the rather silly estimator 10 for all outcomes of the experiment would of course be perfect. However, for other values of lambda, this estimator would perform rather dismally. Thus, we need to find an estimator which is typically close to the true value of lambda for all possible values lambda can take. One reasonable thing that we could demand is that whatever the true value of lambda is, the expectation of the estimator equals lambda. This means that if you were to repeat the experiment of measuring the 12 decay times many times over and calculate the estimator again and again, your average estimate should approach lambda. We want this to be valid for the true value of lambda. But since we do not know which value lambda has, we just insist on this for all values of lambda. This way, we are certain that for our value of lambda, the expectation of the estimator equals lambda as well. An estimator satisfying this condition is called an unbiased estimator. Suppose you draw from a distribution depending on the parameter lambda. An unbiased estimator for this parameter lambda is an estimator T such that the expectation of T equals lambda for all values of lambda. Notice that for each value of the parameter lambda, the distribution of the outcomes, and thus of T, is different. So the expectation of the estimator T varies as well. The definition of unbiased estimator tells you a bit of how you want this distribution of the estimator to vary with lambda. Now, let's get back to our estimator of 1 over the average. By the law of large numbers, we know that the expectation of the average equals 1 over lambda. But since 1 over x is a concave function, Jensen's inequality tells us that the expected value of 1 over the average is more than 1 over the expectation of the average, which is lambda. This means that our estimator is biased. On average, it's too high. How can we resolve this? Well, because we know that the average of several exponential distributions follows a gamma distribution, in this case we can explicitly calculate the expectation of 1 over the average. We find that this expectation equals 12/11 times lambda. So if we use 12 over 11 times 1 over the average as an estimator, the expectation of this new estimator u does equal lambda for all values of lambda. This new estimator is thus an unbiased estimator for lambda. Unbiasedness of an estimator is thus a nice thing to have. But how can you decide which of several unbiased estimators is the best? And besides, is it really necessary to have an unbiased estimator? Or could a biased estimator sometimes be a better choice? In class, you will explore these questions. Before class, I'd like you to think about the following question. Suppose we draw 3 random numbers from the set 1 up to n, where capital N is some unknown parameter. The probabilities for drawing each of these n numbers are equal. You can now calculate the expected value of the average of these 3 numbers, and you might already see that this expectation depends on the parameter n. Can you turn this average into an unbiased estimator? See you in class.